Hello everyone. This is a continuation of our series on kinematics. Till last video we discussed the equations of motion, how it is derived from calculus method and how it is applicable only for the cases where we have uniform acceleration. Now let's solve some problems on those topics, right? So this is a problem on equations of motion. So the problem states that a bullet going with a speed of 350 meter per second enters a concrete wall and penetrates up to 5 centimeter before coming to rest. Find the deceleration, right? So when bullet will penetrate a wall, obviously the wall will restrict its motion and there will be a deceleration, right? So we need to find how much is the deceleration. In question we are given that it penetrates that wall up to 5 centimeter and then it goes to rest. So these are our initial conditions which are given. Using that we need to find acceleration, right? So let's draw the diagram. Every physics problem needs to be started with a diagram, right? So let's say this is a wall, right? This is a wall, right? And let's say this is a bullet. This is a bullet, right? So this bullet has initial velocity which is u as 350 meter per second, right? So this is its motion trajectory. It hits the wall, penetrates it something till, let's say this distance is 5 centimeter, right? So this bullet penetrates this wall till 5 centimeter, right? And here at this particular state, now my final velocity v is equal to nothing but 0 meter per second. It has come to rest, right? So you see, what are given quantities to us? We are given with initial velocity, we are given with final velocity, we are also given with the distance it is traveling, right? Okay, so u is 350 meter per second, right? V is 0 meter per second. Distance traveled by the bullet is 5 centimeter, right? Which is nothing but 0.05 meters, right? Let's talk in SI units only. We need to find what is acceleration. What is acceleration, or in this case, deceleration, right? Or retardation. So using all these variables, what formula comes to your mind? We know that the third equation can only help us, which is v square equal to u square plus 2as. We have all the values and we need to find a here, right? Let's put up the values and find what is a. So 0 equal to nothing but 350 square plus 2 into a into 0.05, right? So a becomes what? Minus of 350 into 350 by zero point 0.1, right? This is what it is. And if you solve this, what should be the value? Should be something like 12.10 to the power 5 meter per second square. You see, the value of acceleration or deceleration is a very huge quantity, right? This is a very huge value. It means the bullet from 350 meter per second instantly goes to 0 meter per second, and this much amount of deceleration is created, right? So this is acceleration. So the deceleration will be nothing but the magnitude, right? 12.2 into 10 to the power 5 meter per second square, right? Let's discuss another problem. So acceleration of a cart started at t equal to 0 second varies as below. So this is how acceleration versus time graph for any given cart, right? So we need to find how much distance that cart travels in the 30 seconds duration, right? So if you see this 30 seconds duration, you see there are three sub levels of motion, right? Three different levels of motion, right? From 0 to 10, this cart is traveling with a acceleration, positive acceleration of 5 meter per second square. From 10 to 20, this particle has zero acceleration, right? And from 20 to 30, this particle is, or this object is decelerating with 5 meter per second square, right? So there are three different divisions in this motion, right? Let's talk one by one, right? Let's talk one by one. Let's name these divisions, right? Let's say this is my first division of this journey, this is my second, and this is my third, right? This is my third. So we need to find distance traveled in 30 seconds. So if I Find distance travel in this first part of motion, then second part of motion, then third part of motion, and add them up. I'll get distance travel in whole 30 seconds, right? Now catch here is, don't forget that these three parts are connected to each other, right? So initially my velocity is 0, right? For first part, let's say initially my velocity is 0, but the velocity at the end of my first part will be the initial velocity for second part, right? Don't forget that. And velocity at the end of second part will be the initial velocity for third part, right? So I'll be using 1, 2 and 3 suffix to indicate these parts, right? Okay, so let's see. Initially u1, which is initial velocity, and it falls in first part, is given as 0 meter per second, right? u1 is 0 meter per second, and acceleration in first part is 5 meter per second square, right? 5 meter per second square. Now if I need to find distance traveled in first part, the time for all three parts is 10, 10, 10. The duration is 10, right? You can see this is also 10, this is again 10, and this is also 10, right? So time is 10. So distance travel in first part of motion is uit plus half ait square, right? So u is 0, it becomes 0, so this becomes half into 5 into 10 into 10, right? So this becomes nothing but 250 meters, right? This becomes 250 meters in the first part, right? Now at the end of this first part, let's say at this point, let's name this a and b at point b, right? And let's name this at c and d. So at point b, where it is ending the first part and starting the second part, so what is the final velocity? You can calculate final velocity using this expression, v equal to u plus at, right? So u is 0, it becomes 5 into t, which is 50 meter per second, right? Which is 50 meter per second. So here the object has velocity as 50 meter per second, right? So initial velocity for my second part becomes 50 meter per second. Now you see, in second part acceleration is what? Sorry, in second part acceleration is 0 meter per second square. The particle is not at all accelerating. So final velocity will remain same as initial, which is again 50 meter per second, right? And if you need to find distance, you can simply calculate, distance equal to speed into time. There is nothing, no acceleration and all. You can directly use that formula, right? So what is distance in second part? So you take any speed and then multiply it by time. So it is nothing but 50 into 10. So this becomes 500 meters, right? So I have solved the second part as well, right? So in second part it travels 500 meter. First part it traveled 250 meter. Now taking the third part of motion, right? So what is the initial velocity for the third part? So this is nothing but what is that velocity at the end of second part will be the initial velocity for third part, right? So initial velocity for third part is nothing but 50 meter per second. Acceleration is given as minus 5 meter per second square, right? Now what I need to find? I need to find the distance traveled. So distance is nothing but it becomes ut minus half at square again, plus half at square is the formula, t square, right? Let's say this is third acceleration for third. So this becomes 50 into 10 plus half into minus 5 into 10 into 10. This again becomes 250 meters, right? So net distance is 250 plus 500 plus this 250, which becomes 250 plus 500 plus 250, which becomes 1000 meter. So in this 30-second journey, this cart will travel 1000 meter, which means 1 kilometers, right? So this is how we can calculate these type of problems where we have varying format of accelerations, right? Okay, right. So let's solve one more problem on this. A particle traveling in straight line moves with initial velocity v1 for a distance x and uniform velocity v2 for next equal distance, right? Find the average velocity, right? So we are given two velocities here, right? Let's draw the diagram for the problem. So the motion is segregated like this. So for the distance x, first x, the particle has velocity v1. For distance again, same as the previous, the particle has velocity v2. Now we need to find what is the average velocity, right? So in problems like this, let's not go that by the way that average velocity will be the average of both the velocities, right? Let's first understand the problem. What is the meaning of average velocity, and then we'll solve it, right? So average velocity, like average velocity is nothing but it is total distance by total time or total displacement by total time, right? Total displacement by total, sorry, total time. Now you see, again there are two parts of this motion, right? There are two parts of this motion. This is first part and this is second part, right? So you see, if I talk about total distance, this is nothing but x plus x, right? 2x. What about total time? So time will be different in both the parts, right? For the first part, for first part, you know there is no acceleration. You can directly use distance, speed, and time relation. So time for the first part will be what? Distance by speed. Time is distance by speed. So x by v1. So for second part, what will be time? T2 will be x by v2, right? Now we can easily calculate what is average velocity. So average velocity is nothing but x plus x is total distance, and t1 plus t2, which is x by v1 plus x by v2. This is my total time in the motion. So it becomes 2 upon 1 by v1 plus 1 by v2. X will cancel out each other, right? So if I solve it analytically, it becomes 2 v1 v2 by v1 plus v2, right? So this is how we will find the average velocity for these type of motion, right? Okay, right. Let's solve one more problem on the motion. So the problem states that a ball is dropped from height 19.6 meters above the ground, right? So it rebounds and raises till same height. Taking starting point as origin and vertically downwards as positive x-axis, we need to plot distance or displacement versus time and velocity versus time, right? Let's draw the diagram to understand the question first. So this is surface of ground, and from some height which is at 19.6 meters from this ground, a ball is dropped vertically downwards, right? A ball is dropped vertically downwards, and we need to consider this point as origin, right? Approximately this point as origin, and this as my x-axis for this particular problem. So from where we are dropping the ball is origin, and vertically downward is x-axis, right? We need to plot what? We need to plot distance or displacement along the x with respect to time, and then velocity with respect to time. Initially the ball is at 19.6 meters from this ground, right? But it is at x equal to 0 if we see with respect to coordinate, right? And how the motion will be, if we think the motion of this ball, this will start from x equal to 0, this will come down to till ground, and this will be the maximum displacement for that ball, which is 19.6. After it hits the ground, it rebounds back in the same motion and reaches again to 0, right? Okay, this is how distance will vary with respect to time, right? If I need to find the time it will take to reach the ground, I can simply say that initially u is nothing but 0 meter per second square. Sorry, u is nothing but 0 meter per second, right? It is starting from rest, clear? And since it is dropped from some height, we assume that it is starting from rest. And you know acceleration will be nothing but 9.8 meter per second square, which is due to gravity. Distance is 19.6. So if I apply s equal to ut plus half at square and find the time from here, this term is 0. So time will be what? This becomes 2 into 19.6 by 9.8 t square. This becomes 4. T is 2 seconds. So in 2 seconds, it will take 2 seconds for this ball to hit the ground, right? It will take 2 seconds for this ball to hit the ground, clear? So let's understand how the motion of this ball will actually look like, right? So we just discuss x is nothing but half at square, use 0 for the downward motion we are talking as of now. So for x will be what? Half into g into t square, right? Which is nothing but 4.9 t square. And when x is 19.6, the t becomes 2, right? At 2 second, it will hit the ground. So if I talk about t equal to 0, right? T equal to 0 second, x is nothing but 0 meters, right? You see, at initially it is at origin. This is my origin, right? This is my origin for this question. Initially it is at origin, right? What about at t equal to 1? At t equal to 1, x will be where? X will, it will be till, it will move till 9.4.9, 4.9 meters, right? Then what happens is at t equal to 2 seconds, it hits the ground. At t equal to 2 second, it hits the ground, right? Clear? Now analytically, if we try to plot these points on graph, right? If we try to plot these points on graph, we will get some nature, right? But we need to also understand how the rebound motion will look like, right? It will hit the ground, it will rebound, right? So how the rebound motion will look like, right? So if I talk about the rebound motion, right? So this expression is for the downward journey, right? Downward journey. What's in plate for the rebound motion, right? So in case of rebound motion, the initial velocity will not be 0, but what will be 0? 0 will be my final velocity, right? It will go and stop at that particular point, right? Okay, so let's calculate what is the initial velocity for the rebound motion, which is basically the final velocity of the initial downward motion, right? So final velocity for the downward motion is will be given by v equal to u plus at gt. So this becomes what? T is 2, it is 9.8. This becomes 9.8 into 2. So this becomes velocity also becomes 19.6 meter per second, right? So at the end of this motion, the velocity will be what? It will be 19.6 meter per second, right? Now let's calculate what will be the expression for distance for the rebound motion, right? What will be the expression for distance for the rebound motion, right? Okay. So for the rebound motion, which is the upward motion, the initial velocity is 19.6, which was the final velocity for the downward motion. So if I calculate the expression for downward motion, right? For sorry, upward motion, the x will be nothing but, if I write it here, x will be ut minus half ut plus half at square plus half at square. So this becomes 19.6 t minus half into 9.8 into t square. What is why it is minus? Because since it is moving upwards, so this becomes 19.6 t minus 4.9 t square. So this becomes this becomes expression for my rebound motion, right? So this is the expression for rebound motion, which is upward motion, right? Now if I plot x versus t for this upward motion, right? Now you see at t equal to 4, if we place t equal to 4, x becomes 0, right? So I'm ignoring 3 for now, but if I place t equal to 4, x becomes 0, right? If we place t equal to 4, x becomes, which means the particle has reached back to its mean position from where it started the motion, right? From where it started the motion. Now if I plot everything graphically, right? So you can also calculate at t equal to 3 where the position will be, right? But if you plot graphically, this is x and this is t. So at t equal to 0, x is at 0. So this becomes 0, 0, right? At t equal to 1, x is at 4.9. So at t equal to 1, x will be where at? it will be somewhere at 4.9. Let's say this is 1 comma 4.9, right? At t equal to 2, x is at its maximum distance, which is 19.6. So let's say this is 19.6, right? So this is how the journey looks for the downward motion, right? This is how the journey will look for the downward motion, right? Similar for the upward motion, if you see, so this is for the downward motion. For upward motion, if you see, at t equal to 4, this comes back to the 0th position, right? So for upward motion will look somewhat like the mirrored image of this, right? If I draw it properly. So this is how position time graph will look for this particle, right? Right. So this is how it looks for the upward motion, where the x varies like 19.6 t minus 4.9 t square, right? The x varies with time like this, and here x varies with time like x equal to 4.9 t square, right? So this is how we can plot the distance and time. What about velocity and time? Simple way we can also calculate velocity and time as well, but for simplicity I'll just differentiate and plot velocity, right? So for downward motion, right, for downward motion, x is 4.9 t square, so velocity is nothing but dx by dt. It becomes what? 9.8 t. This is velocity. For upward motion, displacement is 19.6 t minus 4.9 t square. Velocity is dx by dt. It becomes 19.6 minus 9.8 t, right? So this is for upward motion, right? Now if I plot this graphically, right, if I plot this, just notice one thing, that the velocity is a linear function of time, right? So the graph will look like a straight line, right? This is very clear. The graph will look like a straight line, right? Okay, right. So distance and velocity relation for downward and upward motion looks like this, right? So 0 to 2 interval, second, the time from 0 to 2 is downward motion time, right? And this is what it applies for this. Time equal to 2 to 4 is for the upward or rebound motion. And time equal to 2 is the reference point for rebound motion, which is actually the initial point for rebound, which is kind of time equal to 0 for that motion, right? For overall motion, this may be the second, but for rebound motion, that will be the 0th initial second. So if I plot from 0 to 2, which is v equal to 9.8 t, you see at t equal to 0, v will be 0, right? At t equal to 1, v will be 9.8, right? Let's say somewhere over here, 1 comma 9.8. At time equal to 2, v will be what? It will be 19.6. So somewhere over here. So if you join all this, since it is a linear, so this will be a straight line, and this is how it looks for the downward motion, right? What about upward motion, right? So for upward motion, my velocity will be negative, right? So because I'm going in the negative x, right? Because this was my positive x, which is my downward motion. My upward motion will be against this, and this, hence it will be negative, right? And if you see, this will exactly look like this, but in the negative side, negative x, right? This will exactly look like this, but in the negative x, right? This will be my upward motion curve, and you can also place the values here and find it out. So since at t equal to 0, which is the second, the velocity will be 19.6, which is again here 19 minus 19.6, and this is plus 19.6. And at time equal to 4 seconds, which is the time equal to 2 seconds for upward motion, this becomes 0, and hence this comes back to 0. So this is velocity time curve for this particular problem, right? Okay. And next topic for us is motion in a plane, which is very important topic for this particular chapter, kinematics, right? So we just discussed motion in a straight line, and we discussed that to represent motion in a straight line, we need just one coordinate, right? Either x or y we can use and represent motions in a straight line. But motions in a plane means this is a two-dimensional motion. We will have movements along two dimension. So there might be a movement along positive x also and positive y also simultaneously, and hence we need two coordinates to specify these type of motions, right? So now let's see how things are varying in these type of motion, right? Let's see graphically, right? So let's say this is how coordinates of any particle, moving particle, looks like, right? And I'm representing, this is plus y and this is plus x, right? This is, let's say, the coordinates look like. Okay, at any instance, let's say at any instance of time, the particle has coordinate of x comma y, right? At any instance it has coordinate x comma y. Let's say at another instance it has some coordinate which is x plus delta x and y plus delta y, right? So it has shifted in x also, it has shifted in y also, right? So if this is my a point and this is my b point, right, you see the displacement along x is delta x, right? The displacement along x is delta x and the displacement along y is delta y, right? You can see the displacement x from a has become x plus delta x in b. So displacement along x is delta x and displacement along y is delta y, right? So if I need to calculate net displacement for this, right? If I need to calculate net displacement for this, let's write everything in the position vector form, right? So when it was at a, the position vector will be what? X I cap plus y j cap, right? Let's bring vectors back. We need vectors a lot here. When it goes at b, the position vector becomes x plus delta x I cap plus y plus delta y j cap. This is position vector at b. Net displacement, right? Net displacement will be what? If this is a and this is b, this is my net displacement, right? This is my shortest displacement. So net displacement, which is RAB vector, is nothing but, let's say this is RB and RA. This becomes final vector minus initial vector, right? And which becomes delta x I cap plus delta y j cap, right? So this is my position vector or the final displacement, which is delta x I cap plus delta y j cap. Delta is the displacement along x axis and delta y is displacement along y axis. Now this is how we talked about displacement. If we talk about velocity, right? So how velocity will look like? So velocity is nothing but, let's say, differential of this with respect to time, and it becomes differential of delta x with respect to time I cap plus differential of delta y with respect to time j cap, and let's say this becomes vx I cap or delta v I cap plus delta v y j cap, right? Now you see velocity also has component in x also and y also. Delta vx is the component along x-axis, delta vy is component along y-axis. Again, acceleration also, if I talk about, acceleration will look something like delta ax I cap plus delta ay j cap, right? So acceleration also has components along both the axes, which is along x-axis also, which is along y-axis also. Now the few things are concerning here, because velocity, acceleration, position, everything has components in two directions now. So whatever equations of motion we learned just before, how can we apply here, right? How can we apply here? So let's see how can we apply equations of motion here, right? So we'll discuss now how can we apply equations of motion for motion in a plane. We just discussed velocities can have component in both the direction, acceleration can have component in both the direction. So all the vector quantities can exist in both the directions now. So how can we use equations of motion there? So we will take one direction at a time and then apply equations of motion. So let's see how. For, let's say, x-axis, the equations of motion will be like vx equal to ux plus ax into t. Sx equal to uxt plus half ax t square. Vx square equal to ux square plus 2ax into sx. This is equation of motion for x-axis. Again, for y-axis, this becomes like Vy equal to uy plus ayt, sy equal to uyt plus half ayt square, Vy square equal to uy square plus 2ay sy. So what is Vy, uy and suffix? So Vy is the final velocity along y direction, uy is initial velocity along y direction, ay is acceleration along y direction, sy is displacement along y direction, right? Time is same in whatever you take. Again, same for vx, ux and ax, right? Now let's take an example for motion in a plane. What is the best example for motion in a plane, right? So the best example for motion in a plane is projectile motion, right? Projectile motion. So projectile motion is when you project something. So when you throw something obliquely, like with an angle, so either you can throw something directly vertically, that is not a projectile motion, right? That is directly you're throwing in one direction. But if you throw something obliquely, let's say a ball obliquely, so if you throw something obliquely, it will go down, it will start going up till some height, then it will come down and come back to ground, right? This is the trajectory we call. This is how it will follow, right? Let's say this is from here, you are throwing this with some velocity with some angle, let's say theta angle, right? And this is how the nature of curve of the motion, right? So this projectile motion is the best example for motion in 2D, right? You see, at every point you have velocities in two directions, right? Here acceleration is only in one direction, because acceleration is only because of earth. In x direction there is no acceleration, but velocity, you see, you take any point, you have that directions in velocities in two directions, right? So this is a projectile motion. So this point is point of projection from where you have thrown the object. This is the point of projection, and this angle is the angle of projection, right? And the path with which it follows is the called as trajectory of projectile, right? Projectile is the object which you are throwing, so that is projectile, and its motion is called projectile motion, right? So we will discuss this motion in detail in coming lectures. What is projectile motion? How can we find different points on this curve? How can we judge what type of motion it takes? How can we find what is the maximum height it is reaching? How can we find what is the maximum range it will reach up to? And so many terminologies in coming lectures, right? And we will also solve more and more problems on the motion of these projectiles, right? Till then, thanks.